if I had to pick 3 topics that you learn about in Gen Chem 1, 2, that's the reason why you're taking this class. IMFs is important, sure. Hydrogen bonding, sure. It's kinetics is probably top. And then this thing called equilibrium, and then this thing called electrochemistry. Those are probably the 3 main things that you need to get from this class. Okay. Kinetics is about how fast reactions happen. So we are going to spend several days on this. And in fact, your next exam, I know our first exam is this Thursday, right? It's over chapters 10 and 11. The next exam is, I hope, next Thursday. And it's going to be just chapter 12, one exam just for chapter 12, because it's that big of a chapter. So let's do our first section. Reaction. That's my abbreviation for the word reaction, right? Reaction rate. So these are numbered. Lecture set 5 starts off our kinetics chapter. Let's talk about what is a reaction rate. A rate is a measure of change over time. That's a rate. How does something change over time? Specifically for chemical reactions, okay, what we're looking at is going to be the change in amount. And even more specifically for amount, the amount that we're going to be looking at is the molarity concentration, because molarity is the chemist's preferred concentration, okay? So we are going to look at changes in molarity. And this might be a good time to teach you this. Whenever I put a symbol, a formula symbol in these square brackets, in chemistry, that means I am talking about that molarity. The square brackets means molarity in chemistry. And we're going to look at both reactants and products. So we're going to talk about how does the reactant concentration change? How does the product change? Over what? Time. A rate is about change over time. So what are the units of a rate that we're going to see? Well, we're going to have molarity on the top of this unit. Molarity per, and then whatever time unit you're measuring in. What's common? Seconds, minutes, hours, days even. I mean, it's whatever unit of time you're measuring in. Sometimes you may also see the units not written as a fraction. You may see it written as a product. What do I mean when I say unit time to the negative first? Inverse seconds, inverse minutes, inverse meaning 1 over the second, because our seconds are on the bottom of our calculation. Our time is on the bottom. Guys, sometimes you might even see the molarity unit split into moles per liter. And some references will put the rate as moles times inverse liters, so liters on the bottom, times inverse time. They'll just write all the units like that. Sorry. Okay. I don't care. It doesn't matter to me. They're all valid. I probably tend to default to this when I write, but you guys will see these as well. What happens to concentrations of, let's say, reactants? What happens to concentrations of reactants over time? Think, just, it's not a trick question. It should be common sense. As a reaction is happening, what happens to the concentration, the amount of a reactant that you have? You get less of it. Why? Because it's literally changing into something else. It's going away. Reactants disappear over time, right? Product concentration does what over time? Yeah. So sometimes we'll use this phrase. Products, we can say appear. That's not how you spell that word. That's how you spell that word. I had an E on the end. Products appear, or we might say they form over time, right? So what we want to be able to do is first in our kinetics journey, write something called just a rate expression, okay? The first thing I'm going to teach you to write. For individual reactants or products. Let's look at an example equation. Here's an example reaction. What is this compound? Do y'all know? H2O2? It's a good thought. Hydrogen peroxide. Hydrogen peroxide, H2O2 is called hydrogen peroxide. Let's recall some Gen Chem 1. What kind of reaction would you classify this as? Say it again, Jeff. Decomposition. Separation. Yes, very good. Splitting. Very good. Decomposition. One reactant splits apart into two new substances. Okay. Let's try to describe how the concentration of our reactant, because we only have one here, is changing over time. Any kind of change. How do we calculate a change? Final minus initial. So what does it mean? You guys know now, right? If I write H2O2 in the brackets, I'm talking about the what? The molarity of that compound. Let's say I take the concentration at my final time, whatever I choose that to be, and I'm going to subtract what it was at my initial time, T1, whatever I'm choosing that time to be. Maybe it's time 0, maybe it's 10 seconds, whatever it is. That's actually what we're doing. We are finding the slope of a graph. Over what? Over time. Final minus initial, right? T2, final time minus initial time. There we go. That's how you would calculate, start to calculate the what? The rate of this reactant disappearing. let's condense this. We can write this in a shorter way, can't we? Let's use our delta. Right? And let's use our delta. Change in concentration over change in time. Yeah? Yeah. Now, you guys should be able to reason this. If this is disappearing over time, then at our second time point, this number, this concentration is smaller than it was at this time. So when I subtract a smaller number from a bigger number, I'm going to get a negative answer, right? Here's the thing, though. Rates are positive values. Think about a rate like speed. Are there negative speeds? There's only positive speeds. Rates are only positive values. We don't express rates as negative values. So because rates are positive, if this math is going to give me a negative answer in my, what is this called that we're writing? In my expression, a reactant includes a negative sign in the expression to counteract the math that we're going to do. Okay? A reactant rate includes a negative sign in the expression. And so this right here, this, what I wrote right here, would be what is known as what? A rate expression. It is the rate of, and now this, the disappearance, I'm going to keep writing this word to beat this into your head, but I wouldn't actually normally write the rate of disappearance of. I would just write the rate of the what compound it is. Because I understand if it's a reactant, yes, it's disappearing. Okay. What about what words would be used for water and oxygen? The rate of appearance or the rate of formation? What would those rate expressions look like for these particular reactants? For these particular products. Correct. Each substance has its own rate of disappearance or appearance, okay? So what would be the rate of, I think I tend to use the word formation a lot, so I'm going to use that word. The rate of formation of water. You tell me what to write. What would I be writing for this reaction? It's the change in what? Concentration of water over whatever time period I'm looking at. And this change is positive because products do what? Form over time. So sometimes we might actually still include, just for clarity's sake, I might go ahead and intentionally put a positive sign right there. Okay. What does this expression represent? The rate for water. And similarly, the rate for O2 would look the same way, right? That's how I would calculate the rate for oxygen. Okay. Here's another nifty thing. What's going to happen to the rate itself of my reactant over time. What's going to happen to the rate itself? Take a look at this. Take a look at this data. Look at this data. So over time, we know that the concentration will decrease. Yes? Here it goes from 1 to 0.5 to 0.25. Okay, the concentration is decreasing. So look at what's happening to the change then. The change is also decreasing. And if the change is decreasing, then the rate is decreasing. Can y'all visualize what would that look like on a graph? Would it look like this? Okay, there's concentration, there's time. Is this a straight decrease, a linear decrease? It is not. If it was, then the rate would be the same the whole time. What is it instead? Okay. See? Over time, we get less and less concentration, but the rate changes. What are we calculating here? If I say change in this over change in this, well, I'm kind of talking about if I take this concentration at this time and then this concentration at this time, I'm finding the slope of this line that I drew. What is this called? Secant line. This is a secant line. What is this called? At this exact point, I draw a line that touches that curve and only that one point. That is what is known as a tangent line, right? Okay. I'm not going to have you draw these lines, but I'm wanting you to understand what we're calculating here, okay? What we're calculating is often what is known as the average rate, right? Average rate. What is the change over this time period? If I calculate it at a tangent point, instantaneous rate. At a tangent point, that's instantaneous. At that moment, there's the rate. We do both in chemistry. Okay, we do both. You'll see it referred to as both. I'll talk about both things. This would be an average, right? That's an instantaneous. Okay. So what we want to be able to do, though, one more thing. If I do this instantaneous rate at time 0 for the reaction, that's what's known as the initial rate. Okay, you'll see that phrase a lot too. Here's the initial rate of the reaction. So what does that mean? It's the rate right at when time starts. Okay. What we want to be able to do is relate the rates of disappearance and formation for everything in a reaction. Because overall, there is only one rate of a reaction. So now I am trying to think about all the pieces kind of together. Okay. This reaction has one rate. But each of these individual rates are relative to each other. Can I erase all of this? Okay, so what I wanted to do right now is write a relative rate expression. Okay, I'm thinking about how all elements, all compounds' rates are related to each other. Okay. I said there's only one overall rate of the reaction, right? There's just one rate. So how does each piece fit into that rate? We're going to relate each individual product and reactant using their coefficients. It all comes back to moles, right? How many moles of this do you have? We balance my equation, right? Okay. So let me just first write how it looks, the relative rate, and then we'll kind of, we're going to do examples and delve into it a little more, okay? This is how you would classically see a relative expression written. What coefficient was in front of the peroxide in the equation that we're looking at? It had a coefficient of 2. And it's a reactant, so it has a negative sign. So see what we do? We put the coefficient as a coefficient in front of the rate. One over the coefficient. And why do I have the negative sign there? Because it's a reactant. And in fact, I'm actually going to rewrite this a little. Never mind. I said I was going to show you the way you'll traditionally see it. Okay, the way you would traditionally see it is the negative sign out in front, and then 1 over the coefficient, and then your rate expression. Okay. Whatever this number comes out to be, you calculate this number, you multiply it by 1/2, take the negative of it, so it's a positive value. Okay, whatever this value comes out to be has to be equal to, what was the next thing in our equation? Our product. Water. How many, formation of water, how many waters did we have in our balanced equation? 1 over the coefficient. Why is water's value positive? Because it's a product. Why is it 1 over 2? Because that was the coefficient. Okay, so this number has to equal this number, has to also equal what? Oxygen's relative rate. What is the relative rate? The relative rate is putting 1 over the coefficient in front of the change you calculate. All 3 of these values are the same. When you take the relative rate by multiplying 1 over the coefficient, they all are the same value because they're all just the rate of the reaction. Relative to each other, they're the same. Relative to each other, they're the same. So I actually prefer to rewrite this relative expression this way. This is the way I prefer to do it. Because to me, I can see it better if I, in parentheses, put the negative because what did I teach you guys? This negative change in concentration divided by change in time is the what? What is this? I can still calculate this number by doing what? Final minus initial, right? Final minus initial. Throw a negative sign in front of it. And then I can do what to that number? Multiply it by 1/2. See what I mean? This is calculatable. Word. It's not, is it? You can calculate this. And you can multiply by 1/2, can't you? Boom, there's your answer. There's your relative rate. You want me to finish writing it real quick with this, Scarlett? Okay. This has to equal what? 1/2 of, and say what this means in words. The rate of, what word are we using for products? I said let's use formation. This right here is the rate of formation, right? Of water, isn't it? Calculatable. I gotta find a better word than that, y'all. Okay, I can't think of one right now. And then I do what? I take that number that I calculate and I do what? Take 1/2 of it. Equals what? 1/1 of positive change in O2 over time. And that is the what? Rate of formation of oxygen. All right, Scarlett, you will do it now. Okay. Let's practice. In-class examples. We're gonna do 1 through 3. Very first one is I just want you to practice writing relative expression. How would you write the relative expressions for these 3 substances in this equation? What kind of reaction is this? Excellent. Combination reaction. Or sometimes it's called a synthesis reaction, but I like combination. That's what I say these days. Yeah, you know what that means. I'm combining, guys. That's what we're doing, right? Okay. What do we know about reactants rates? Their expressions have a negative sign, right? What do we know about product rates? Positive sign. What do we know about how we write the rate? Delta, change in concentration, over delta T. And then because we're making them relative to each other, we include what? 1 over the coefficient in front of the rate. See if what you are writing is this. And you can write it this quote unquote classical way, but I prefer this way because then I can really see how these rates are relative to each other. For whatever reason, putting those parentheses there helps me understand, okay, this is the rate. This is the rate. But relative to this rate, it's 3 times as fast, or it's half as fast. What, you know, I mean, that helps me verbalize it, I guess. Make sure you guys understand, why did I put all of these? You understand why all of those symbols are written right there. Yeah. If you don't, ask. And then if you want to, you can go ahead and look at, if you've written that, go ahead and be looking at number 2. Number 2, I gave you a reaction. 2A, very simple. 2A forms B. Okay. And then I gave you some time and concentration data. See what you can calculate there. Let's figure out the average rate. How do you calculate a rate of anything? Change in concentration over change in time. If it is a reactant, then when you calculate this rate, you have to put a what in front? Negative sign. So I'm going to look at the change in the concentration of A over what time period first? First one says from 0 to 10 seconds. From 0 to 10 seconds, right? Okay. Final minus initial, yes? What's my final? What is the concentration of A when it's 10 seconds into the reaction? 0.625, what unit? Molar. Okay, negative in front, 0.625 molar minus initial. What is it at time 0? 1.000 molar. Divided by 10 minus 0. Right? This is so easy. Well, I say that. It's going to get a lot harder, but this part is easy. This part is easy. Yeah, we can just stay at this level. That's fine. That's all we need. We're good. What do you get? 0.0375 molarity per second, because those are our units for rate, right? So again, I tend to default with the fraction. Is it also perfectly fine to write molarity times S inverse? Absolutely, that's fine. Okay, let's do it now for our next time period. 10 seconds to 20 seconds. Okay. From 10 seconds to 20 seconds, I can see our concentration change. What should I see happen to the rate that I'm calculating? The rate should be getting slower, smaller, right? Because this concentration has changed. It does. For this rate, I got 0.0265. Yeah. Molarity per second. Okay, now let's do some relating. Let's relate. Guys, did I give you any information about the concentration of our product B? I only have data for the reactant, but we now know how to relate the two things, don't we? What is the relative rate expression between A and B? What is the relative rate expression between A and B? Okay, for my A, if I take half of its rate, right, that has to be equal to what? The rate of formation of B. 1/1, because why? Our coefficient for B is 1. I'm going to write this, even though I understand it's 1/1. Okay, but I'm going to include it because you always got to do 1 over the coefficient. For B, for forming B, what does that rate expression look like? Forming B, positive, right? Again, I'm writing all these symbols. This is a lot of math. I mean, this is what math is, right? This is what math is, right? But guys, at its heart, what does all those little symbols right there mean? It's the rate of A. At its heart, what do all these little symbols right here mean? Rate of B. If I want the rate of B, how do I mathematically solve for this? I'm going to show this step because if this wasn't 1/1, it would matter. How do I get rid of this 1/1 fraction on this side? Multiply by the reciprocal, right? That's the reciprocal. Yes, that's what I'm doing. Yes. Okay. I asked about B during what time period? 0 to 10 seconds. Didn't we just find the rate of A from 0 to 10 seconds? What was it? This number right here. From 0 to 10 seconds. Here's the rate of A. So that's the number I use. That's the number I plug in. I calculate this rate, and then I multiply it by 1/2, and I multiply it by 1/1, and that gives me the rate of B. Say it one more time. You want me to write? I'm going to write the math. I'm going to write the math. Okay, so here, so I'm solving for just this portion of this equation, right? I'm solving for the rate of formation of B from 0 to 10 seconds, right? That's my time period. Okay. So this whole thing is the rate. And that equals 1/1 times 1/2 times this number. 0.0375 molarity per second. I'm about to get right in front of you. Okay. So again, this is the rate of B. And numerically, what does it equal? Half that number, right? Half that number. .0188 is what I got when you round for sig figs. Half. B forms half as fast as A disappears. Or you could say it, A disappears twice as fast as B forms. Yeah, okay. What about C? What about the second part, third part of that problem? The instantaneous rate. So we talked about this, right? Average means I'm, calculating over a time period. What does it mean if I say the rate is instantaneous? Like at that one point in time. How is that found? The only way right now to find that would be to look at a curve and draw a tangential line. So I'm not making you guys do that. I'm telling you, here's the rate. Here's the instantaneous rate, okay? So disappearing A at 15 seconds, here's its rate, 0.023. Well, at that same moment in time, what's the formation rate for B? Think about what we just did. What is true? B forms half as fast as A disappears, right? Is that always true? Yes, because it's always a 2-to-1 mole ratio. Yes, that is always true. Always, always. So if you have the rate for A, what do you do to get the rate for B? Half of it, right? This exact same math that we just did, except I'm giving you a different rate of A to use. I'm giving you this rate of A to use in your math. So at that moment in time, B is forming at a rate of what? 0.012. Half the rate that A is disappearing. Try 3 real quick. And then I think we're gonna call it for today. And I've got to tell you to look at the next section on your own tonight. But let's look at 3. Huh? Well, let me see. Maybe I'm. Okay, so I'm doing my 0.023, right? Divided by 2. Okay, but so it has to have 2 sig figs, right? So why am I dividing? Huh? Oh, girl. Okay, don't do it. Sig figs. The calculator gives 0.0115. With 2 sig figs, that rounds to 0.012. Okay. Okay, look at 3 real quick. Let's try some numbers other than 1s and 2s. Okay, here's this whole big ass equation. What kind of reaction is this? Y'all don't know yet. That's fine. Actually, never mind. It's a redox reaction. And we're gonna learn you remember that? Okay, we're gonna learn all about that later this semester. But I'm only interested in 2 species from this reaction. What am I interested in? Br minus, the bromide ion, which is that guy. And then I'm interested in bromine, which is that guy. So if I'm interested in 2 different species and I'm talking about their rates, I have to write the relative relation between those 2 rates. So let's start with that. How do we write the relative rate expression for bromide ion and bromine? Okay, so write it. You guys tell me what to write. 1 over what? 1 over 5. And then the parentheses negative. Okay, so then remember, how are you guys going to see? You're going to see these written with the negative sign out in front, right? If you go look at another resource, they probably are going to just put the negative sign out in front. I just prefer to put it with the 1 over 5 negative change in BR minus over change in T. This has to be equal to 1/3 okay, change in BR2 over delta T. Yes. What did I give you in the problem? The rate of disappearance of BR minus at a moment, so this would be the instantaneous rate, is 3.5 times 10 to the negative 4th molarity per second. Where is that number? That number that I just read off is what in this? Is this right here, right? Good. So, what am I solving for? This. I want this rate. How am I going to solve that rate? Get rid of the fraction by multiplying by the reciprocal. Nope, that's not the reciprocal, Gary Poe. This is the reciprocal. It's time to stop. It's time to stop. It's time to stop. It's time to stop. That's fine. We're about to stop. It's time to stop. Okay, so that's how I got rid of that. So I'm basically doing what numerically? 3 divided by 5 times this number. Take that and multiply this by 3/5. Yes. You guys are getting this so well. I'm so proud of y'all. I'm also spending a lot more time on this first section than I normally do, because in the past, when I've tried to just be like, okay, let's move on, this foundation means a lot more than I realize sometimes as we go on later in the chapter. Like if you have this foundation down, what is a rate? What is a rate? I think it's going to help. So even though this is putting us a little bit behind on my schedule, I'm always behind on my schedule. So what else is new? It's fine. I get so that is what I got. So here is my positive delta BR2 delta T, which is the rate of formation of BR2. I also got that number. I got 2.1 times 10 to the negative 4 molarity per second. And y'all got that as well, right? Excellent. Perfect. Beautiful. Okay. So what I would like for you guys to do before class tomorrow, well, it would really help if you did it before class tomorrow. Is it absolutely imperative to understand what's going on in the next section? Not really, but at some point it is. Okay. Section 2, factors that affect rates. I have 5 different tweaks you could make to make a reaction go faster or slower. Okay. Maybe y'all can think of one big thing that you can change that would make a reaction go faster or slower. Temperature, absolutely. Most reactions, if you increase the temperature, guess what's going to happen to the rate? It's going to go faster. Of course, there could be exceptions and weird things, but I mean, generally, that's what would happen. So that's what this section is. I have 5 things that you can change to affect a rate. I want you to know those 5 things and understand if I change it this way, up or down, whatever, this is what will happen to the rate. Okay, cause and effect. What's the cause and effect of each one? They're all listed here. You can just go through the slides. I have a couple of videos embedded, like short videos showing the examples. You can watch those or not. I don't really care about that. You're not going to be quizzed over that. Nature of the reactants matters. What physical phase the reactants are in matters. Why did most of our reactions happen in aqueous solution? When they're dissolved in water, those molecules are moving around more freely and they're free to collide, interact. Whereas if I just have a hunk of solid and another hunk of solid, I mean, it depends, but probably not going to do anything. Okay. Things like that. Temperature, concentration. The more concentration you have, the faster the reaction usually goes. And then this last thing, something called a catalyst, which we are going to talk more about in this chapter, but we're saving that for the last section in more detail. But know that that can increase the reaction rate. Okay. No, I do say at some point you really do need to. But if you didn't do it before class tomorrow, I think you're okay for what we're going to do tomorrow. Okay. And so then tomorrow we're going to start the section 3. We're going to talk about a law. So we wrote rate expressions today. Tomorrow we're going to learn how to write laws about rates. Okay. And what do you guys need to be doing? I wanted to see what I talked about today, like if I had a change of heart and decided to talk about colloids, but I didn't. So I was waiting to post your quiz for chapter 11 until I decided what I did this morning. But so now, you stay. Okay. Okay, that first set was due last night. So that's due date's gone now. You can still finish questions if you need to, but second set is Wednesday night. And so now I will post the chapter 11 quiz on active. I think I only have 7 questions. Okay. That's a smaller quiz. I don't know about the time yet. Was the 75 minutes adequate on the last one? I'll probably do that again. Why not? When is this going to be due? Thursday morning, the morning of the test. I am going to open the first chapter 12 set. I don't know that any of you guys will actually start working on it tonight. I'm not really anticipating you doing it, but I'm going to go ahead and open it. When will it be due? I don't know yet. Friday? But I think it also has the rate laws, which is what I had hoped to get to today, but I didn't, and that's okay. So I wouldn't think you'd be able to finish it for sure, but I'll go ahead and open it. Tentative Friday due date. No, because you're going to have another set to be working on. Okay. Remember that solutions worksheet? I told y'all, if you want me to get it graded and back to you by tomorrow, you got to turn it into me today. Maybe that's something you want to finish down in the lab while we're making our ice cream. Don't forget we were making ice cream. Okay. Or you can turn it into me tomorrow, but then I'm not going to get it back to you before the test. So, we're going to go down and make some ice cream using freezing point depression as our science background. And I want you guys to finish making your cooling curves from your data yesterday. Get your delta T, get how much the freezing point depressed. Get your delta T so you can solve for the molar mass of your substance. So we're going to have just kind of a work day making our ice cream. If you don't want to make the ice cream, you are not, this is not a grade. You're not obligated to make the ice cream, but why would you not want to make ice cream?